Hello everyone, I am Calc, and today I'm going to be solving two problems using a technique called mass point geometry, which could prove to be very useful on the upcoming AIME. So, if you're interested in learning what it is, how does it work, how do we use it in a variety of problems, you're in the right place. Starting off, we have a problem that was tailor-made for it. The 2014 MathCounts Chapter Team Round, number 10. We're given a diagram much like this, and we know that AF is 3, BF is 2. Switch markers really quick, sorry about that. BD is 2, CD is 2, and AE is 5. And we want to know the ratio of BG to EG. So, the way mass point geometry work is that we translate all these ratios along different sides of the triangle into masses of the points, and we use that to find them more masses, which gives us more ratios. It goes in kind of a one-to-one correspondence. So we'll start with the masses of A and B. Since AF to FB is a 3-to-2 ratio, the mass of A to the mass of B is in a 2-to-3 ratio, the exact opposite. We're going to use A is 2 and B is 3, just sticking up nice whole numbers. We could use fractions, we could use decimals, we could use multiples of pi to the power of e if we wanted, but we're going to stick with whole numbers for this problem. Then we have B, D, and C. BD to DC is 2-to-2 or 1-to-1. So their masses must be equal because they're also in a 1-to-1 ratio. 1-to-1 flipped over is still 1-to-1. Next up, now we have masses of A, B, and C. If I want to, I could find EC using changing these masses into ratios. But instead, I'm going to find the mass of E so we can find BG to GE. Now, the rule of mass point geometry is when you have a side length and two masses, a mass for each end of the segment, you can add them to find the mass of the middle point. So 2 plus 3 is 5, obviously. So we have B has a mass of 3 and E has a mass of 5. So if this is in a 3-to-5 ratio, BG to GE is in the opposite ratio, or 5 to 3. So that problem was rather simple using mass point. The next problem is less so. It comes from a series of mock exams that you might have heard of if you're looking for a good practice on the internet. It's called the Mildorf Mock AIMEs. These were written in 2004 and they still stand up. They're still harder than any AIME that has ever come out, and they probably will be for a long time. So if you want some harder practice just to get you ready for the day, make all the problems seem easier, I would highly recommend them. Go look for them. Easy Google search. Anyways, we're going to be doing a problem from the second exam, number 15. A geometry number 15 on a super hard AIME. That sounds like death, but it's really not. Let's start looking at it. So we have BC is 13. CA, or AC, same difference, is 37. And AB is 40. Now at this point, we don't have any of these side lengths, so we can't really find the masses yet as definite numbers. But we do know something else about D, E, and F. They all meet at the circumcenter. And for those of you who don't know what the circumcenter is, basically, if we were to draw a circle containing the points A, B, and C, it would have the center right here where those lines meet. That's the circumcenter. So we know that, and we want to find the value of 1 over AD plus 1 over BE plus 1 over CF. Sorry, I need to write that lower. We're looking for, I'll write it this side. 1 over AD plus 1 over BE plus 1 over CF. So, that sounds really complicated, and when I first started this problem, I thought I was going to have to whip out a bunch of obscure identities with cosines and tangents and whatnot. I had to find some random similar triangles or cyclics or something, and then eventually get the answer. But we really don't. We can just use mass points. To start off, I'm going to say point G right in the middle here has a mass of 1. So A plus D, C plus F, and B plus E all have to be 1 when we assign masses to those. We also know, since this is the center of a circle that touches A, B, and C, the distance from here to A, and here to B, and here to C is all the same, and it's the radius of the circle. So we're going to use a capital R to represent that. The circumradius of the circumcircle with a circumcenter. Those are all very important terms that you should know coming into the competition. So we have these are all capital R. I'm just going to say this is lowercase a, lowercase b, lowercase c. At this point, I don't know anything about them. I'm going to try to find out stuff about them. So, let's say I just wanted to assign A is lowercase a and D is capital R. I can't do that because that sums to A plus R, and we need it to sum to 1. But I can divide both of them by A plus R, and now it sums to 1. Nice and fine. So A is A over A plus R. D is R over A plus R. Then we have this is C over C plus R. And this is B over B plus R. And we have our masses. Now we can do something pretty cool. We know that D must be the sum of B and C, and G is the sum of A and D. Therefore, G is the sum of A and B and C. So we're given that A over A plus R plus B over B plus R plus C over C plus R is equal to 1. Now, this is close because A plus R is AD, B plus R is BE, and C plus R is CF. But we're not quite there yet because we have these annoying terms up top. But what if I turned A into A plus R minus R? Then that's all over A plus R. If we break this up, we get 1 minus R over A plus R. The other terms are 1 minus B over B plus R. 1 minus R over B plus R, sorry. Yeah, 1 minus R over B plus R, and 1 minus R over C plus R. So if we add all of them up, now we get 1 and 1 is 3, like the Beatles song says, minus R over A plus R, minus R over B plus R, minus R over C plus R is equal to 1. We move things around and we get R 1 over A plus R plus 1 over B plus R plus 1 over C plus R is equal to 3 minus 1 is 2. And so we now know what we need to find, because 1 over A plus R plus 1 over B plus R plus 1 over C plus R is 1 over AD plus 1 over BE plus 1 over CF, which is what we're looking for. So what we really need to find is the circumradius, so we can find 2 over R. But we don't know the circumradius, we just know these sides. So, how do we find the circumradius, you're asking? Area formulas. To start off, we're going to be using Heron's formula. Very nice formula. We start with the semiperimeter. 13 plus 37 plus 40 is the perimeter, divided by 2 is the semiperimeter. This is 50. 50 plus 40 over 2 is 45, right in the middle. So we have a semiperimeter of 45. Then the formula is that the area of our whole triangle is 45 times 45 minus 13 times 45 minus 37 times 45 minus 40. And we can simplify this stuff to 45 times 32 times 8 times 5. 45 times 5 is 225, which is 15 squared, so we can move that 15 out. 32 times 8, that's 16 times 2, 16 divided by 2, so they're going to multiply 16 squared, so we get 15 times 16, that's 8 times 30, or 240. So, now that we know the area, we just need another area formula to take us from this and this to our circumradius. Fortunately, one actually does exist. The area of a triangle can be given by the product of the sides over 4 times the circumradius. So we just move stuff around. Going to move R here, going to move A here. So this is 40 times 13 times 37 over 4 times 240. So, cancel these out and we get 13 times 37, which is 39, 91, 481 over 24. So, now we just need 2 over r for our final answer. So, this is rather easy to plug in. We get 2 divided by 481 over 24 is equal to 48 over 481. And we are done. The official solution for this uses, like I said before, a lot of complex trig identities and nonsense like that to get to this point here. But we just use math points to get there in a few minutes. So that, my friends, is the power of math points. If you enjoyed this video, be sure to like and consider watching some others, subscribing, leave a comment down there to tell me what you think. I appreciate all constructive criticism. And I will see all of you next time.